Hello everyone, and welcome back to the Quarantine Lectures. Dr. Heinz with you. Today we're going to continue our discussion on material science and engineering with our discussion on material properties. Hey guys, welcome back. So when we talk about the properties of a material, what do we mean? What we mean is really how that material behaves, what makes that material what it is, right? If we press on it, if we do some sort of external stimuli to it, how will it respond? So what I'm showing right now over the screen are groups of material properties. Essentially, all properties of solid materials can be grouped in one of 6 main categories: mechanical, electrical, thermal, optical, magnetic, and chemical. Now you notice, of course, that mechanical is the largest group there. It includes density, strength, tensile strength, hardness, toughness, and so on and so on. Stuff that we are fundamentally more familiar with, right? And this is, talking about how something will stand up, right? If I hit it, will it break? If I drop it, will it shatter? Stuff like that, right? Stuff we're more familiar with. We then have electrical, which we definitely talked about in circuits, which is electrical conductivity. Right, as you guys know, right, how easy it is to get electrons to flow through said material. We also have thermal properties, some of which we talked about in thermodynamics, right, through heat transfer. How easy is it to get heat transfer? Is it an insulator? Is it a conductor? We then have magnetic properties. The only one there is really how magnetic is it, right? Is it magnetic? Is it not? Optical properties, there are a fair amount there. What are the color? What's the absorbance, the transmittance, right? Obviously, if you're looking at a glass, that would be ideal for looking through. Something that would be more opaque is not. Also, does it have fluorescence, right? If we hit it with an external stimuli, will it glow? Last but not least, we have the chemical properties: reactivity, combustibility, surface energy, and corrosion resistance, right? This would be basically if we leave something out in the rain, will it rust? How easy is it to catch fire? And stuff like that. So let's start by looking at that big box there, which are the mechanical properties. And the reason that box is so long is because there's a lot of different ways that a material can behave under a load, right, which is an external force. The mechanical properties provide important information to how that material will perform under certain situations, right? It's how we decide to use a metal for a certain application or to use concrete for a certain application, something like that, right? Fundamentally, also, and we were talking about this in our bridges section, material has to be strong enough to actually do what we want it to do, right? We wouldn't use our silly putty, for example, to build a bridge to cross the Columbia River. Okay, and it also, in addition to actually being strong, it also has to be durable for long enough, right? We want our buildings to last. We want our bridges to last. And the materials that we choose are ultimately chosen for a particular reason and because they have a combination of mechanical properties, right? Again, you wouldn't want something to just be strong but brittle, or you wouldn't want something to be strong but not able to weather the elements, right? So we have to look at a combination of all of those properties together to make the right decision. So let's do a quick review of how loads are applied to materials. We have tension when applied to a material. In fact, let's go back to our silly putty example, right? If I'm applying tension to a material, what I'm doing is I'm pulling on it, right? So this causes elongation in the direction of the applied force, called a tensile force. On the other hand, we have compression. This is due to a compressive force, right? Shortening in the direction of the applied. We also then have shearing, right? And this one becomes a little harder to show, but would basically be like if I was to put it in my hand and go like this. What happens is the top goes one direction, the bottom goes the other direction. What you have is materials being kind of torn apart, right? And then we also have torsion, which is a very special example, which is where we are twisting it, right? So we have all those examples there, and we've talked about those before, right? But again, remember, tension is this direction, compression is this direction, shearing is this direction, and torsion is this direction. All right, and that leads us to deformation and fracture. So if a sufficient load is applied to a material, it will cause that material to change in shape, right? That's exactly what we were doing with our silly putty. This is known as deformation, right? When something starts to change shape under the applied load, it starts to deform, okay? If the applied load is large enough in magnitude, it can then cause the material to break. And once it breaks, we call that fracture. It's the separation of the material into two or more pieces under an applied force. Most mechanical properties that we're going to go through, and we are going to go through them, describe a material's tendency to or not to deform or fracture in a certain manner. So first up, we have strength. How strong is our material? And this is the ability of a material to withstand an applied force without bending, breaking, shattering, or deforming in any way. So fundamentally, what it's saying is, how much force do I have to apply to this material? How much force can this material withstand before it breaks, right? So in the example we're showing here, load is applied, something with high strength will not break, something with low strength will break under the same force. Next up, we have elasticity. This is the ability of a material to absorb a force and flex in different directions and then return to its original shape. So in our example of silly putty, once we stretched it, it did not go back to where it was, right? However, you could use something like an elastic band, for example, that if you pull it, it will snap back, right? A rubber band will often do that. But again, if you pull a rubber band far enough or hard enough, it can still stretch. So what we're seeing here is we have a load applied. An elastic material will snap back, maintain its original shape, and an inelastic material will deform. Next, we have ductility. This is the ability of a material to deform under a tensile stress, such as the ability to be pulled into a wire, right? So of course, copper wire is a thing. If you heat it up, we can get it to stretch, but obviously if we do it normally, we would break it, right? So again, that's how we process the material. Next, we have plasticity. This is the tendency of a material to change in shape permanently without breaking, right? So plasticity, to be clear, is not plastic, right? Plasticity is how much it can change without breaking, right? How flexible is it versus how rigid and hard is it, right? That's really what this is a measure of. So if we were to put a load on something with high plasticity will change shape, it will flatten in this case. Something with low plasticity will resist or ultimately break. Malleability is the ability to be reshaped without breaking, such as being hammered into a sheet, right? Metals or something, or metals and that type of material are very good at being malleable, right? You can pound copper into a sheet, but if you were to try to pound concrete into a sheet, it would not, it would break, right? So something that can easily be flattened by pounding on it would be malleable. Something that easily be reshaped is malleable. Something will break versus being reshaped is non-malleable. Now we have toughness. This is the ability of a material to absorb energy and to deform without breaking or shattering. All right, so in this case, what we're showing is our rod is being hit with a hammer in one sharp blow. This could also represent being dropped onto the floor, for example. Something with high toughness will take that hit and be okay. Something with low toughness will get dropped onto the floor or will take that hit and it will break, potentially shatter. Now we have hardness. This is the ability of a material to resist scratching and indentation under a compressive force. So this would be, again, what I'm showing here is pushing a screwdriver into a material. If that material is hard, like say concrete or tile or something like that, it will not divot, it won't scratch, it won't indent. If something's soft, like maybe a wood or a plastic or something like that, that will leave an indent, right? So hardness is a measure of how much that will indent under that force. So let's go to Course Handbook, page 56 for a quick sample problem. A material sample as shown below deforms plastically under tension. Of the choices below, which best reflects the sample's final shape after the load is removed? So what we have here is we have our original sample, it's just this rectangular piece of material. So after it deforms plastically under tension, does it look the same? Has it stretched in the middle? Or has it compressed and gotten fat in the middle? The answer is B, right? The reason that B is the answer is because it says that it deformed plastically. A has not deformed at all. C did deform, but it very clearly deformed. It got shorter and fatter. So it very clearly deformed under compression. Right? And this was deforms plastically under tension. So high plasticity is marked by permanent deformation. A did not deform. And the only one that deformed under tension was B. So B is our correct answer. Now let's go to Course Handbook page 57. A cylindrical sample of material as shown below undergoes completely elastic deformation under a shearing stress. Now remember, a shearing stress is where the top and the bottom are taken in different directions. Of the choices below, which best reflects the sample's final shape after the load is removed? We have A, we have B, and we have C. So A is the correct answer here, and the reason is that completely elastic deformation means the sample returns to its original shape. B has deformed. It did deform very clearly. The top and bottom went in different directions, which would have supported our shearing stress. And C did not only deform, it actually broke. It broke to the point of fracture. So again, remember that elasticity, high elasticity, means the ability to return back to its original shape after the load is removed. A is the only one that fits that criteria, so A is the correct answer. For our last sample problem, let's go to page 58 in our handbook. A cylindrical sample of a material with low toughness is dropped. From the diagrams below, select the one that would best reflect the sample's final shape. A, where there has been no deformation, B, where there has been some deformation, and C, where there's been complete material failure, like shattering. Okay, so remember, low toughness. Toughness is a measure of how much a material can take before it breaks. Something with low toughness then would be very apt to break, and that is why C is the correct answer. Toughness is the ability to absorb energy without breaking. A experienced no change, B deformed but did not break, and C shattered and broke, so it displays lowest toughness. So that caps off today's discussion about materials properties. Join us in the next lecture as we continue our discussion on material science and engineering.